algebraically today. So I think we got the recording going, and we're going to take a look at how to do this one algebraically using the definition of absolute value. Should be really fun. So we're looking for the limit as x approaches 0 from the left of f of x, which is absolute value of x over x. So blue, that seems like a good color. Let's do blue. If we are looking at the values as x approaches 0 from the left, what can you tell me about this absolute value piece of it? Or first off, what can you tell me about the values of x that we will be plugging into this function?
They'll be negative.
Excellent. X is, no matter what, less than 0. And part of our function is the absolute value of x when x is less than 0. So what does the absolute value of x equal when x is negative, according to the definition of absolute value?
X.
Something positive.
Right. So sometimes it's x and sometimes it's not x, and it depends on the values of x. So what we're going to do is I'm going to put a new page in here, and I'm going to tell you if I'm looking at x less than 0, the absolute value of x is always equal to the opposite of x. And if x is greater than or equal to 0, the absolute value of x is equal to x. Think about any number you want to plug in. Pick a number that's greater than or equal to 0, like 8, right? Absolute value of 8 is 8, right? The absolute value of x is just x. But up here, for something that's less than 0, if I'm looking for the absolute value of -8, what is that? That's 8. It's the opposite of -8, right? So anytime you plug in a negative, you get the opposite of what you started. Anytime you plug in a positive or 0, you get the same thing. So that's effectively what we're doing here. We're saying I'm plugging in x values that are negative into the absolute value of x. So I should get the opposite of x. So if we could simplify down absolute value of x into simply just negative x, or the opposite of x, for this particular limit, that should allow us to simplify this to opposite of x over x. And now if we try to plug in 0 into this, what do we get? We get 0 over 0, which is still indeterminate, which is still a problem. But it means, what can we do? We can cancel those x's out and say this is now the limit as x approaches 0 from the left of just -1. Anybody know what the limit as x approaches 0 from the left of -1 is? What does that equal?
-1.
It equals -1. And that's what we got yesterday when we did that problem graphically, isn't it? We looked at this and said, as we approach 0, we're at -1. Does that make sense? Does that process make sense to everybody or no?
Yeah.
Any questions on that? No? Everybody good? All right. So what about when we approach 0 from the right? That means that all of my x values are
Positive.
positive. They're all greater than 0. And when I take the absolute value of something that's positive, I get just that thing that I started with. So this limit, the limit as x approaches 0 from the right, absolute value of x over x just becomes x over x, which is just 1. Yep. Everybody good there? So we see algebraically how to do that, and that should help you with a few of the problems that you're probably looking at in the assignment that's due tomorrow. Does that help or no? Is that good?
Yep.
What about this last one down here? Since the limit from the left is -1 and the limit from the right is 1, this limit
Does not exist.
does not exist. Same deal as yesterday, right? Good. All right. let's move on then to this piecewise defined function. Take a look at this. So I'd like you guys to take a couple seconds and sketch the graph of this piecewise function real quick. I'll do the same. I'll graph it also. As best I can, trying to draw on my laptop screen here. Oh, that doesn't look like a piece of a parabola at all. No, neither does that. Neither does that, but we're going to leave it. All right, that's what your graph should sort of look like, right? 3 minus x, which is just, negative x plus 3, slope of negative 1 with a y-intercept of 3, until we get to 1. And then at 1, the value is 4. And then when we're greater than 1, we have this, supposed to be a parabola going up there. It doesn't quite look like the right-hand side of a parabola because drawing on my laptop screen is not easy. So we're going to do this algebraically and we're going to do it graphically. It should be pretty easy. As x approaches 1 from the left, let's graphically look at it. As we look at going towards 1 from the left, what are we getting close to?
Two.
We're getting close to 2. Everybody see that? Okay. And if we were to do it algebraically, we need to look at the piece of our function that includes the values that are less than 1. And so this would just be 3 minus 1, which is 2. And if we do it from the right-hand side, we can look at it. What's it approaching? As we approach x equals 1, the y values are approaching
2.
And we would use this piece of the function, 1 squared plus 1, giving us 2. And so is there a two-sided limit here?
Yes.
And it should be the same as the left and the right-hand limits. In fact, it must be the same as the left and the right-hand limits. Everybody good with that? Pretty straightforward? Okay.
Yep.
Cool. So we're going to run through a few rules for limits real quick, and then I'm going to introduce the first theorem that we're going to deal with, and then we'll use it a couple of times and we'll be done for the day. It's actually going to be a pretty easy day. So the first rule, and we're going to talk a little bit about the rules, and we're going to really get in depth with them tomorrow. But the first rule that we want to talk about today is that the limit of a constant is always just that constant, which I think should make sense because this constant is, if this constant is just a function, that function should just be a straight horizontal line. Like for example, as the limit as x approaches 3 of 7, well, if this is just a horizontal line at 7, all right, we'll call this y equals 7. No matter what x value I'm approaching, the y value is always 7. I could be approaching 3, I could be approaching 1,000, right? The y value is still going to stay as 7. So the limit of a constant is always the constant. Right? The limit as x approaches -4 of 10 is 10. The limit as x approaches 10,000 of pi is pi. Right? The limit of a constant is always just a constant. Any questions on that? All right, cool. You want to know that. Somewhere on the YouTube that I put up, you'll find my students last year convinced me that I should make an ASMR video of me repeating the limit of a constant is a constant over and over again. So you can find that if you're having trouble sleeping at night. This will make it worse if you listen to that. Next rules for limits that we're going to talk about are all of these. So as long as our limits as we approach a of f and g both exist, we can separate or combine together our functions using either addition, multiplication, subtraction, or division. We can pull the two functions apart or put the two functions together, however we need to find the limits. So if I have two functions added together, I can evaluate the limits separately if I want to, or if I have two functions being multiplied together, I can evaluate the two limits separately. For example, if I had the limit as x approaches 3 of 2x squared, I could rewrite that as the limit as x approaches 3 of 2 times the limit as x approaches 3 of x squared. And we should get the same answer. Now we do the same thing with an addition. So if I have 2x plus 5, I could do the limit as x approaches a of 2x plus the limit as x approaches a of 5. Same thing with subtraction, same thing with division, as long as the denominator limit does not equal 0. Everybody good with those four? Okay, good. And then this last one doesn't look very important, but it is. So, and we can prove that this is true using what we know about the limit of a constant. But this is telling me that the limit as x approaches a of 3x, let's say, is the same as 3 times the limit as x approaches a of just x. Okay. We can take the constant that's being multiplied by a function and pull it out in front of the limit so that it's no longer part of the limit, which doesn't seem very exciting or very useful probably, because just leaving the 3 in there, if I'm trying to evaluate this at 5, it's just 15, 3 times 5. Pulling the 3 out doesn't make it any easier. But when we start dealing with a bunch of trig functions, it's going to make a lot of it possible to do, whereas it would have been impossible without this rule. Good?
Wait, so it's saying like the constant of f of x is equal to the limit of the constant f of x?
So what it's saying is if I have the limit of a constant times any function, then I can pull the constant out of the limit and put it in front. So that example with the 3x isn't maybe the best example. Suppose I had something like the limit as x approaches, I don't know, pi over 4 of 7 tangent x. We could just plug in the pi over 4 and get a value, but what this is saying is this is equivalent to 7 times the limit as x approaches pi over 4 of just tangent x. Does that make sense? Does that answer, that answers your question? Okay, cool. Which I'm sure you're all sitting there thinking, well, what's the point, right? Plug in pi over 4 and I can get my answer either way. True. But we're going to develop some very important special cases of some limits for trig functions that will require us to not have these constants in here, that we're going to need to be able to take them out. And we'll do that tomorrow. So on top of that, we've got some other rules here with exponents and radicals and all of that. If I have a limit of a function being raised to a power, I can find the limit of just the function first and then raise it to the power afterwards. So this is a simple example of that. I could rewrite this as the limit as x approaches 2 of 3x plus 4, and then raise that answer to the 5th power, and it is the same as what I would have gotten had I done the whole thing initially. Once again, doesn't seem real exciting with these simple like binomials that are being raised to powers, but when we throw trig functions in there, it's going to be a necessity. Any questions on that one? Same thing for roots. We can pull the roots outside if we want to. And anytime we have positive integers for our roots, we can just go straight through and evaluate the limits. We don't have to worry about doing anything fancy with them. But we can still pull the powers and the roots out of it. And so I'm not going to really pause on this too long. Just know that you can pull those roots and those powers out. If you want to read through this again later, I'll have it all posted up. But what I'd really like to get to after we do this really stupid basic problem that I kind of should have just deleted from this slideshow is the really important theorem. So first, evaluate that limit. So if we're going to plug in 8 here, what's 8 to the 2/3 power?
Is it 4?
It is. I just want to make sure you all know how to do 8 to the 2/3 power. How do you do 8 to the 2/3 power? It's the same as 8 with a cube root around it, squared. You could do the squared part first or the cube root part first. I suggest doing the cube root part first, right? It's going to give you 2 squared, which is 4, which is maybe easier than doing 8 squared, which is 64, obviously, but then cube rooting that. I mean, you should know that that's 4 also, but yep. So we got 4 plus 3 times square root of 8, which is 2 root 2 if you simplify that radical, over 4 minus 16 over 8, which is 2. Our denominator is just a 2, so we can divide the 4 by 2 and the 3 times 2 root 2 by 2 and get 2 plus 3 root 2. That's about as simple of a limit problem as you should expect on some tests that I might someday give you. Pretty straightforward one though. All right. How many of you think limits are easy so far? For the most part. Most of you, I hope. They're going to start getting more complicated now. So hopefully you're okay with that. This is our first real theorem. This is called the Sandwich Theorem or the Squeeze Theorem. And it used to not show up on the AP test very often, but the last few years they've thrown some stuff in with it. So we're going to make sure we have a pretty good, clear understanding of it this year. Sometimes there are functions, like for example, the function h of x that we're going to deal with here, that we have difficulty evaluating the limit at a certain value of a. One trick we can use to help us evaluate some of these limits is we can find a function, and in this case our function g of x, the red one, that is always greater than or equal to h of x. And we can find another function, in this case the blue one, f of x, that is always less than or equal to f of x. And if we can sandwich the function h between g and f, and then find a point where the limit as x approaches a of g is equal to the limit as x approaches a of f, then that will tell us that the limit as x approaches a of h is the same as those other limits, because g must always be above h and f must always be below h. So if the limits of g and f are the same at a certain point, the function that's between them must also have the same limit. It's squeezed between those two upper and lower bounding functions. Does that make sense? If that doesn't make sense, you should say something now. especially since I can't see the looks on your faces if you're looking shocked and confused. Okay. Well, I'm going to assume that you're all okay, and we're going to try and use that theorem to prove that the limit as x approaches 0 of x squared sine of 1 over x squared is 0. So the first thing we should always do when we're trying to evaluate a limit is what?
Plug it in and see if it works.
Plug it in, exactly. Plug it in and see what we get. So we plug in 0, we end up with 0 times the sine of 1 over 0. And you may be sitting there thinking, well, great, it's 0 because it's 0 times something. But the sine of 1 over 0 is undefined. 0 times something that is undefined is not something that's possible for us to do. Even though it's 0 times it, it doesn't necessarily mean that this exists and that it's 0. So we can't just assume that. Unfortunately, this doesn't work. So we have to do something else. And what we're going to do is we're going to use the sandwich theorem. And in order to use the sandwich theorem, we're going to first take a look at what the graph of this function looks like. Maybe. There it is. You guys see it on Desmos now?
We see
Sort
it.
of. All right. We're going to zoom in a little bit so we can kind of get a better idea of what it looks like. It looks kind of like the one we did of sine of 1 over x the other day, where it's oscillating back and forth a whole bunch of times as we approach 0. But this time, those oscillations are getting shorter each time. They're getting smaller, right? Smaller heights to them. And it sort of appears like, if I zoom in here, it looks like it's approaching 0. Would you guys agree?
Yes.
Yes, all right. Somebody responded. I like it when I get a response. That's nice. So what we need to do then is we need to find a function that's always above this and a function that's always below it that have the same limit at x equals 0. Any ideas on how we can do that?
Could you multiply like the function you have now by a constant? Because wouldn't that have the same limit, just more? I don't know if that made sense.
It makes sense. I understand what you're saying. But unfortunately, it's not quite going to do what you want to do. So yeah, if I go in here and say, let's say 2x, well, I gotta keep this one in here. Let's keep that one and put in 2. You'll actually see that it's not always above it. Sometimes that same function is above and sometimes that same function is below. So if I put a constant in there, that's not quite going to do it. Other ideas?
Can we use like functions that we already know have limits that equal 0 at 0?
Sure.
Like x squared maybe?
Okay, well, let's take a look. Let's look at x squared. So if I throw in, let me zoom this out a little more. Let's throw in x squared. Well, that certainly looks like it's above that, doesn't it? I could zoom in a little. Yeah, it's looking like it's always above it, true? Or equal to it? And so what would the other function be that would be below, you think?
Negative x squared?
That seems reasonable. And it looks like it's sandwiched nicely between those, doesn't it? Negative x squared is always below it or equal to it, it appears, and x squared is always above it or equal to it, it would appear, no matter how far in here I go. True?
Yes.
Okay, now are we sure that it's always above it and always below it?
No.
No. How can we be guaranteed that it is? How can we show that that's always true? What do we know about the function sine of 1 over x squared without the x squared in front of it? Tell me about that function.
The higher or lower that x gets, the smaller y will be?
Say that again, the higher that,
I'm sorry, could you repeat that? It cut out.
I wasn't sure what you had said. I was looking for you to repeat what you'd said.
Oh, yeah. The higher or lower x gets, the smaller y will be?
Not necessarily. Oh, okay. The higher or lower that x. Okay, yeah. So the higher or lower that x gets, if x gets very large positive or very large negative, you mean?
Mm-hmm.
Yeah. So that's gonna get us very close to 0, right, inside of here, and so then we're getting close to the sine of 0, which we can see it's approaching out to 0 to the outer point. But we're more concerned about what's happening as we get close to x equals 0. True? And this is very similar to the sine of 1 over x function that we looked at. But what do we notice about the y values, all of the y values of sine of 1 over x squared?
Between 1 and negative 1.
Right, they're between 1 and negative 1, which I mean, that's true for any sine function, right? If I take the sine of x, what are the values between? They're always between negative 1 and 1, right? Because x is just going to be some number, right? Doesn't matter what I put in here. X is just going to be some number, and I multiply it by the 23 or whatever I have. And then I take the sine of it. It's always going to be between, 1 and negative 1, right? No matter what I throw in there, put in all kinds of, doesn't matter what I throw in there. It's always going to stay between 1 and negative 1.
Wait, so Mr. Bachelor, I have a question.
Yes.
So if it's x squared times sine of 1 over x squared, can you pretend that x squared is a constant and move it out of the limit?
You cannot pretend that it's a constant because it's not a constant. No, you can't do that.
Okay.
You can only move it out if it is actually a constant. Yeah. But what we can do is we can say that the sine of 1 over x squared is always between 1 and negative 1. And then we can add this x squared into here by multiplying all 3 pieces of this by x squared, which is going to give us negative x squared is less than or equal to x squared sine of 1 over x squared is less than or equal to x squared. How do we feel about that? Everybody okay with that?
Yes.
All right, so now what we've got is we've got the function that we are interested in the limit of sandwiched between 2 other functions. It's always going to be greater than or equal to negative x squared, and it's always going to be less than or equal to positive x squared. And so now all we have to do is find the limit of negative x squared and the limit of x squared as we approach 0 and show that they're the same, which they both are. If you plug in 0 to negative x squared, you get 0. And if you plug in 0 to positive x squared, you get 0. And so by the sandwich theorem, the limit as x approaches 0 of x squared sine 1 over x squared is also 0. Does that make sense? Any questions on that process? All right, let's see if you can get this one started. Thoughts on how we're going to get this one started?
Cosine is still between 1 and negative.
Yeah, cosine is just the same as sine, right? It's always going to be between 1 and -1. Everybody agree with that? Take the cosine of any number, it's always between 1 and -1. So all we have to do is multiply all three pieces of that by x to the fourth. And find the limits as x approaches 0 of negative x to the fourth, which is 0, and positive x to the fourth, which is also 0. And since both of those are 0, the one sandwiched between them is also 0. Everybody good with that?
Yes.
Cool. All right, we're going to do one more that's similar to this, but it's going to have a little bit of a twist. It's going to have a little bit of an issue. And this is actually, we're going to stop with this one. This is going to be the last one we do today. We'll call it an easy day today. Send you home early or whatever, even though you're already at home. What makes this one different? Can I still start with this? Sine of 1 over the cube root of x is less than or equal to 1, greater than or equal to -1. And ignore the x cubed part in the middle.
Yes.
I think so. I should be able to, right? So then can't I just multiply all three pieces by x cubed? Like we've been doing with the other one. Like the last one, I multiplied them all by x to the fourth, right? And the one before that, I multiplied them all by x to the second, I think it was.
I don't think you can because x cubed can be negative at times.
Exactly. That's the problem. And what's the problem with multiplying by a negative in this case?
The inequality signs will switch.
Right. So depending on what x values I'm talking about, sometimes the inequality signs need to flip and sometimes they don't. So if x cubed is, let's say, less than 0, then those inequality signs need to flip, don't they? But if x cubed is greater than 0, the inequality signs should stay the same as they are. Do you all agree with that? Any issue with that or no? Okay. I don't think it sounded like somebody might have been trying to say something and cutting out. So hopefully everyone's all right. If not, type it in the chat. So if x cubed is less than 0, what does that tell you about x? X is less than 0. And if x cubed is greater than 0, that tells you that x is greater than 0. True? So when we multiply by x cubed here, we should end up with negative x cubed is greater than or equal to x cubed sine of 1 over the cube root of x is greater than or equal to positive x cubed. And on this side, when we multiply, the inequality signs should stay as they already were. and we should end up with that inequality. Everybody feel okay about that? Okay. So on this piece over here, can I take the limit as x approaches 0 of negative x cubed? Anybody? Can I take the limit as x approaches 0 of negative x cubed?
Yes, you can.
Are you sure?
Wait, what was the question?
Can you take the limit as x approaches 0 of negative x cubed over here on this side? Normally, we should be able to, right? We should be able to take the limit as x approaches 0 of negative x cubed. That shouldn't be a problem, right? But don't we have a restriction going on that left-hand side? We are saying that this is only true when x is less than 0. So if my x values are all negative, can I take the limit as x approaches 0 of negative x cubed?
No, you can only take left-hand limits.
I can only take a left-hand limit of negative x cubed because I don't have an open interval on both sides of 0. I only have an open interval to the left because the only x values that are valid for this inequality are the negative x values. So I can say that the limit as x approaches 0 from the left of negative x cubed is 0, which is the same as the limit as x approaches 0 from the left of x cubed. Does that make sense to everybody? Everybody clear on why we can't do a two-sided limit there? We can only do a left-hand limit? Okay, so that tells us then, using the sandwich theorem, that the limit as x approaches 0 from the left of x cubed sine of 1 over the cube root of x is also 0, but that only tells us the left-hand limit. So over here, what are we going to have to do? We're going to have to do it with a
Right-hand limit.
Right-hand limit, exactly. So the limit as x approaches 0 from the right of negative x cubed is 0, which is the same as the limit as x approaches 0 from the right of positive x cubed. And that'll tell us that the limit as x approaches 0 from the right of our function that we're interested in is also 0. And because the limit as x approaches 0 from the left and the limit as x approaches 0 from the right are the same, the one-sided limits are both the same, that means that the two-sided limit must exist and it must be the same as well. Everybody good with that? It's a little bit tedious there to have to go through all of that to just get 0, but that's the work that would need to be shown because there's two separate cases. Anybody have any questions on that one or any of the other ones we've done today?
Wait, I'm kind of confused on this part. So on the left side, or when you're approaching 0 from negative, so it says negative x cubed is equal to 0, which is equal to the limit of x cubed as x approaches 0 from the left. But like, isn't like 0 cubed negative 0 cubed? Isn't that equal to that's equal to positive, and that isn't like negative like negative 1 or something cubed equal to a negative? I don't know.
Yeah, they are, but the point is that we're getting very close to 0. And so the question is, what's happening as we get very close to 0. And so let me pull up.
Oh, it's approaching 0 then, I guess. Yeah.
Right. So as I'm approaching 0 from the left of, of x cubed, I'm going towards 0, even though it's coming from the negative side, that's fine.
Yeah.
And as I do it for negative x cubed, it's coming from positive numbers, but it's still approaching 0. Okay, good.
All right, got it. Thanks.
Cool. Yep. Any other questions on that one or anything else we've done today? Okay. Any questions on anything that we've done at all so far in the last couple of days from the assignments or anything you have questions on that you'd like to ask right now? Nobody? Nothing? All right, so you have an assignment that's due tomorrow. By the end of the day tomorrow, I think I just put like 11:59 p.m. If you have questions on that between now and whenever I go to bed tomorrow, feel free to send me remind messages about that or email me, but remind's probably better. I'd be happy to help you work through any of the questions you're having. And tomorrow we'll go in and do a bunch more stuff with these trig limits and some more stuff with the sandwich theorem. We're kind of put some stuff together to deal with some more complicated limits. And by the end of the day, Friday, we should be done with all the stuff with limits and ready to move on to our next topic. If you guys got no other questions, you're free to go. Make sure you submit that assignment however you can upload your responses, whether it's printing off a copy of the assignment, filling it out, and then re-uploading it, that's fine. Or if you want to just write it on a separate paper or somehow type it on your computer, it's fine with me, doesn't matter to me. If I, for some reason, can't read it or open the file, I'll let you know and we'll work around it for these first couple just till we get everything settled and figured out. Other than that, you're free to go. If you have any questions that you just need to ask real quick, feel free to stay on. I'll be here for a second and can answer questions, or you can send me a remind later. Have a good day.